Hello guys, and welcome to Mr. Academia. If you've not subscribed to this channel, do well to hit the subscribe button and subscribe so you can get notification on our subsequent videos. Now quickly, in this video we are going to be looking at measurements and basic instrumentation calculations. Alright, so this of course is SLT 104.2 basic instrumentation. All right, this is more like an exam focused class. All right, if you've not watched the previous videos I did on the most likely questions, frequently asked questions in SLT 104.2, do well to go and watch that video. Also, I made a video on resistors in a circuit. Another one is resistor color coding. Ensure you watch those videos on this channel. Okay, and quickly we are going to be delving into measurements. Do well to stick to this video to the end, because at the end I'm going to be exposing major shortcuts in SLT 104.2. okay, so what is measurement? Okay, so measurement is the process of comparing a known value with an unknown value, a known value with an unknown value, or you can say measurement is the process of determining the magnitude of a quantity by comparing it with a predefined standard units. All right, so the unknown value, all right, is being compared with the known value. The known value is like a standard value or a standard unit, okay, of measurement. So basically, when you are using a result, a current result, to compare with something that has actually been there and has been set as a standard over time, that process is known as measurement. Okay, so of course, an example is measuring voltage with a voltmeter. Okay, when you're measuring voltage with a voltmeter, voltage is also called potential difference. All right, so that's an example of measurement. Measuring mass with a weighing balance. Okay, measuring length with a meter rule. Okay, so these are examples of measurement. All right, so that's definition. Okay, that's the definition of measurement. All right, so the next thing we are going to be looking at are key elements of measurement. Okay, so key elements of measurement, more like basic things you need to actually know that entails in measurement. Now there's what we call measurand. Now measurand is defined as the physical quantity that is being measured. Okay, like I talked about measuring voltage, okay, with a voltmeter. The measurand here is the voltage. Okay, the measurand there is the voltage. Measurand is what you are measuring. Okay, now there's another word called standard. Okay, so standard is the reference with which the measurand is compared. Okay, for instance, now if we are looking at voltage, now we have 1 volt as more like a standard value. Okay, when you want to measure pressure, we have 760 millimeter mercury mmHg as a standard value for pressure. We also have 1 atm as a standard value for pressure. We have 101,325 newton per meter square as a standard value for pressure. Okay, if you want to measure volume, we have 22.4 dm cube. We have 224 cm cube. Okay, if you want to look at the electric charge, we have 1.6 times 10 raised to power minus 19 coulombs. These are like standard values for particularly for a given measurand. All right, so it is what is used as a reference point for you to actually compare the measurand. So now, what is an instrument? Okay, so another thing we'll be looking at is instrument. All right, an instrument. So what is an instrument? So an instrument is a device used for the comparison and indication of values. So basically, you use it to compare values, you use it to indicate values. All right, so that is what an instrument basically is. Okay, so it is a device that is used to measure, indicate, or record a physical quantity. Take note of that. That's an extension to the definition. All right, so what is the function of an instrument? Number one is to detect the quantity. If you want to calculate voltage, you're using an instrument called a voltmeter. You want to detect the quantity of potential difference in a circuit. All right, now another one is to convert it into a readable form. Okay, a form that can actually be read. Okay, a form that can actually be interpreted, because it's only something that you have read that you can be able to interpret. Okay, another function of an instrument is to display or record the results. So now let's quickly go into basic instrumentation. So what is the definition of the word, or of the compound word, or of the term, anyhow you want to put it, basic instrumentation? Basic instrumentation. All right, so first of all, instrumentation, okay, refers to the science of developing and using instruments for measuring, one, monitoring and controlling physical quantities. Okay, so you can define basic instrumentation as a science of developing, okay, and using these instruments we've already defined. Remember what we define instruments to be, that they are devices that can be used to measure, indicate or record the physical quantity. So when you study the science of developing and using this instrument for measuring, monitoring and controlling physical quantities, that is basic instrumentation. All right, that is basic instrumentation. So there are four components of basic instrumentation. We have sensors and transducers. Sensors and transducers. This component of instrumentation actually shows how to convert physical quantities to measurable signals. Physical quantities, quantities that are physical in nature. Okay, for instance, length, mass, okay, volume, these are physical quantities. When they are converted to signals that can be measured, sensors and transducers are actually used to do that. Now we also have signaling, we have signaling conditioning systems. We have signaling conditioning systems. All right, so basically they are used to amplify, to filter or convert signals. Remember, the sensors and the transducers are used to convert the physical quantities to measurable signals, while the signal conditioning, they are used to convert these signals to any other form. All right, they're used to amplify. All right, amplification is the conversion of AC to DC. If you check the video I made on frequently asked questions, I talked about amplification. The process of converting AC is alternating current, to DC is direct current. All right, so that is the function of signal conditioning system. All right, so we also have the fourth one. Okay, the third one, okay, because I know there are four of them. So the third one is called display or recorders. Display slash recorders. So the instrumentation feature, okay, in basic instrumentation, display and recorders, they are basically used to show results, okay, to show results. All right, an example of display or recorders are meters, screens and recorders. All right, then the last but not the least, we have what we call control elements. So control elements acts on a particular system. All right, it controls a particular system. Control elements. So basically these control elements are instruments that can be able to more like control a particular system, that if you include them in a particular circuit, okay, they can be able to control. For instance, we have resistors. So resistor is an example of a control element. Why? Because it controls the flow of electric current in a circuit. All right, don't forget that. Now the next thing we are going to be looking at is precision and accuracy. Precision and accuracy. All right, okay, so precision and accuracy. All right, so what is precision? Precision can be defined as a closeness of repeated measurements. These are the keyword: repeated measurements to each other. All right, so when repeated measurements are close to each other, it means that we can say that they are precise. So that is precision. All right, for example, now if we have measurements like 9.2 cm, 9.25 cm, 9.3 cm, okay, repeated. Maybe the first measurement we had after carrying out the first trial was 9.2, second 9.25, 9.3. If you look at these three values, you realize that they're actually close to each other. So the fact that they are close to each other, it means that they have been able to achieve precision. It means that this particular measurement is precise. All right, so the next one is accuracy. So what is accuracy? Accuracy can be defined as the closeness of a measured value to the true value. Okay, remember we have what we call measured value, which is of course also called the expected value. All right, so when the measured value which is the expected value, is close to the true value, the true value is also known as the actual value. All right, so when they are actually close to each other, then we can say that that particular measurement is accurate. For instance, now if we take the length of this board and maybe it gives us like 10 cm, for instance, all right, and of course the true value, that is the actual measurement of this board, is 11 cm, or yes, 11 cm. If you look at it very well, they are actually close. Okay, they are actually close. If we have 10.5, it's also accurate. If We have 10.8 is also accurate. Even 10 cm is not so accurate as 10.8, 10.5, 10.9. All right, they are more closer to this 11 centimeter than the 10 centimeter. So basically, when it comes to accuracy, we don't necessarily have to perform multiple experiments to achieve accuracy. All right, if a measurement is not accurate, it's not accurate no matter the number of times that you perform that particular measurement. All right, so now quickly you'll be looking at errors in measurement. Errors in measurement, if we must look at basic instrumentation, all right, it's very important for us to understand that when you're making use of of an instrument, a basic instrument, when you're performing an experiment, all right, there is likely to be error. So what is an error? Errors are defined as the deviations of the measured value from the true value. So when the measured value from the true value or the standard value, the true value is also called the standard value. It's also called the actual value, standard, true. They are all the same. All right. So when there is a deviation, okay, between the measured value and the true value, deviation more like the gap between them, it's not even accurate, it's not even precise, then it means that there is an error somewhere. Okay, so what are types of errors? We have three types of errors. We have the systematic error. All right, so the systematic error can be defined as the predictable and consistent error which occurs due to faulty instruments, faulty instruments, okay, faulty instruments, then environmental effects, and of course calibration mistakes or calibration issues. All right, so when the instrument that you're making use of, the basic instrument you're making use of for that particular experiment is faulty, it can lead to systematic error. All right, systematic errors are also called determinate errors. You can determine them, you can predict them. You can go to the lab and you see an instrument that is faulty, and you know that, no way, if I use this instrument, there's a likelihood for me to actually obtain wrong measured values and thereby leading to error. The second one is what we call the random errors. Random errors are called unpredictable errors that occurs due to noise, operator inconsistency, or unpredictable environment. So one thing about random errors, they are not determinate. Okay, random errors are indeterminate because you cannot easily determine the cause of a random error. All right, it can actually happen because you probably did not like continue with that experiment consistently. All right, it might be that the instruments are not faulty, calibration is okay, and sometimes you might even be consistent, but still you cannot determine the cause of the error. Okay, then it is called a random error. Okay, so basically, for instance, now when the readings in let's say a digital balance is fluctuating, it's not as if the digital balance is faulty, but it's just fluctuating for reasons that you don't even know. Then it's a random error. And we have gross errors. Gross errors are errors that occurs due to human mistakes. Okay, they are human errors. They are also called human errors. All right, they are called gross, gross, gross errors. So they can occur due to mistakes, carelessness, distraction. You're in the laboratory and you are being distracted, you're taking a particular measurement and you're not focusing on it, then it can lead to gross error. Another cause of gross error is incorrect reading or instrument misuse. Okay, the error is as a result of the fact maybe you did not take reading correctly, all right, while performing the experiment, then it can lead to gross error. Sometimes it can also be due to misuse of instrument. The instrument is not faulty, all right, but you did not use it well. You don't even know how to use it, or maybe you are using it carelessly or nonchalantly. Okay, then it can lead to gross errors. All right, so those are of course the types of errors in measurement. Okay, then the next thing we are looking at, okay, since we are still focusing on basic instrumentation, one very core aspect that you should expect in your exam is types of basic instruments, where we have actually looked at the classes of basic instruments, okay, at that initial moment, okay, in this video, but now we'll be looking at types. Okay, types of basic instruments. Now we have number one, we have two types. We have the absolute instrument and the secondary instrument. What are absolute instrument? Absolute instrument are also called primary instrument. All right, they are used to measure the value of a quantity directly from the instrument, but in terms of physical constants. All right, so when you're measuring a particular value or measuring a particular quantity, okay, in these instruments, they are going to give you results that are based on certain constants. You're measuring length, it will give you a result that is based on a particular constant in the length of a particular object, a particular material. So it is not really a common type of instrument that is used. They are not common. Okay, they require no calibration actually. So basically, examples, we have what we call the tangent galvanometer. We have what we call the tangent galvanometer. Okay, then we have what we call the relays current balance. These are actually rare instruments. These are called absolute instruments. All right, then the ones that are commonly used are called secondary instruments. All right, so they directly measure the quantity and give a numerical value. That is what they do. They will measure the quantity directly, then they will give a numerical value for that quantity. Examples are, of course, we have the voltmeter, we have the ammeter, we have the ohm meter, we have the pressure gauge, we have the potentiometer. Okay, and one thing that is common among these instruments is that they can have either a pointer or a digital display. Okay, either a pointer or a digital display that will enable you to actually see the numerical value of that quantity that you're trying to measure. Okay, so that is that. Now quickly we'll be going into major calculations. All right, I know this is the point you've actually been waiting for. We're going into major calculations, and we'll be focusing on very common instruments that are used in basic instrumentation. We'll be looking at how to actually connect them in a circuit. We'll look at how to calculate these connections. All right, so these instruments we'll be looking at resistors, looking at capacitors, then we'll be looking at inductors. So these are the three instruments that we'll be focusing on. All right, these are the three instruments we'll be focusing on. Okay, so now let's begin by looking at resistors. Okay, so basically, what are resistors? Resistors are actually devices which controls the flow of electric current in a circuit. So or resist the flow of electric current in a circuit. Okay, so basically that's the major function of resistor. In our previous videos, I've been able to give you a background of resistors in a circuit, all right, how to calculate resistors in a circuit and their resistances. Okay, so that's what we'll be delving into. So basically, when we look at resistors, we're looking at resistors in terms of Ohm's law. So the Ohm's law was postulated by Simon Ohm. That's why it's called the Ohm's law. So it states that the current flowing through a metallic conductor is directly proportional to the potential difference across it. So it is given as V equal to I arrow. It talks about the direct proportionality between voltage and current, which means that in a given circuit, as your voltage is increasing, all right, the current is also expected to increase. That's what the direct proportionality means. If the voltage is reducing, the current is also expected to reduce. But when the current is actually increasing beyond control, it is expected that the resistors should be available to resist this rapid flow in electric current in the circuit. All right, so it's very very important for that to be done. Okay, so now there are two ways of connecting resistors in a circuit, but basically we'll first of all look at these parameters. V is called voltage, I is called current, and R is called resistance. R is resistance. Okay, so the voltage is measured in volts. Voltage is measured in volts. Okay, current is measured in amperes, while resistance is measured in ohms. All right, so the symbol is V, here is A, then ohms is like this. All right, I told you in our previous video that the device that is used in calculating resistance in a circuit is called an ohm meter. Okay, an ohm meter. All right, but we have two types of resistors though. We have the fixed and we have the variable. Now, the most common method of calculating resistance of a fixed resistor is by using what we call resistor color coding. You can refer to my video on resistor color coding to understand better how to calculate the resistance of a resistor using the technique of resistor color coding. All right, so that's on a lighter note. Now, let's look at this. Basically, there are two ways of connecting a resistor in a circuit or resistors in a circuit. Now, these two ways are actually also common to that of capacitors and inductors. All right, so basically, we are going to be looking at the connection of resistors, capacitors, and inductors, okay, in series and parallel. And basically, we'll be looking at it individually. So, we'll be looking at resistors in terms of series and parallel. Let's start with series. Now, this is actually the symbol for resistors. Okay, in a circuit, resistor can be like this or can be like this. Mind you, this is different from this. This one is for inductors, this is for resistors. This and this can actually be used interchangeably. All right, both of them are actually correct when it comes to resistors. All right, so don't mistake this for this. All right, so the second one, like I said, is inductors. This one is, of course, resistor. This is also resistor. Capacitors in a circuit are actually like this. This how you know that this is a capacitor in a circuit. But we are not looking at capacitors and resistors. For a start, we are at resistors in a circuit. All right. So resistors in a circuit connected in series. Now, basically, when you want to connect resistors in a circuit, there's one thing you need to commonly understand. Resistors in a circuit connected in series, all right, have the same current. They have the same current flowing through them, but different voltages. They have the same current but different voltages. Okay, so basically the same current, because they are in series, it's the same wire. So it's the same current that is flowing through the wire. The same current flows through the wire, but the voltage, all right, the voltage is different. Okay, so basically this is just a wire connection. We have not even added the resistors. So if we are to add the resistors now in the circuit now, this is how a series connection will look like. So a series connection is something like this, something like this series connection. All right, then you have your voltage. All right, so this is the voltage or potential difference. Okay, or basically this voltage is gotten from the battery. All right, you can also see it drawn like this. Sometimes you see it drawn as a battery like this is your voltage as well. So it's important to understand that these resistors have the same current but different voltages, because why? They are connected in series. Now, how can you calculate the total resistance of these resistors when they are in series? Very simple. Total resistance is denoted as REQ, also known as equivalent resistance. Now, to determine the equivalent resistance for resistors in series, you say R1 plus R2 plus R3. Simple. That way you've gotten them, plus Rn, which means that there can be many resistors. Please, we are not limiting the number of resistors in a circuit to three. All right, so that is that. So basically, we are saying that they have the same current but different voltages. All right, and one thing you must understand is that if now the voltages are different, it means that R1 has its own voltage, R2 has its own voltage, R3 has its own voltage, but you must know the current in the circuit. Basically, it's very important for you to understand that on most occasions, if not all occasions, they will give you the voltage of the battery. They'll give you the voltage of the battery, okay, if they want you to find the current. Okay, but so now remember that Ohm's law is V equals to IR. So if you want to find the current in a circuit where resistors are connected in series, I will be equals to, make isolate to a formula, V over R. So divide the voltage by the equivalent or total resistance and you'll get the current in the circuit. All right, then now if you want to get the voltage for each of these resistors, okay, voltage for each of these resistors, for instance, now the total voltage is 50 volts. I want you to understand that this R1, R2, R3, the resistors now will require different voltages. The only time that they can require the same voltage is if the resistors are equal, have equal resistance. All right. But basically, one thing you need to understand is that all of them would need voltage that will sum up to give you this 50. So how will you know their individual voltage? Simple. You know their individual voltage by say I arrow one. Why did you not say I1? The reason why you did not say I1 or I2, I3 is because all the resistors use the same current. So there's nothing like I1, I2, I3, just I. Now V2 is equals to I arrow 2, while V3 is equals to I arrow 3. Very, very important to note. Okay, I arrow 3. So that's how you get the voltage for each of the resistors in the circuit. All right, so quickly, let's look at parallel connection. All right, let's look at parallel connection. So basically, for parallel connection, when you connect resistors in parallel, you are not connecting them through the same wire like series. You're not connecting them through the same wire like series. All right. For resistors connected in parallel, they have the same voltage but different current because the wires are different. Okay. So the same voltage, okay, is being used. It's more like the opposite of series, the same voltage but different amount of current flowing through them. All right, so that's one thing you must note. So the circuit setup is actually represented as follows. So it looks like this. All right, then of course you can have a battery source here. Okay, so this is your R1, this is your R2, this is your R3, then this is your V, this is your potential difference. So look at this one wire, this another wire, this another wire. They don't have the same amount of current. So now, if you want to actually determine the current that is flowing, knowing that they are different, you want to determine the current that is flowing. Okay, you have to first of all know the total resistance. How will you know the total resistance? Total resistance REQ is not R1 plus R2 plus R3. It's not equal to, rather, okay, it is 1 all over rho eq equals to 1 over rho1 plus 1 over rho2 plus 1 over rho3 plus 1 over rho So basically it's the inverted form of your resistances that will give you your equivalent resistance. But please, the mistake a lot of persons make is that by the time they have added this, they will say it's their final answer. It's wrong. The equivalent resistance, when you have added whatever you get here, you still need to do 1 over, because you're making ROEQ sorry to a formula. Okay, now for instance, now if you have 1 over ROEQ equal to 0.5, your ROEQ now will be equals to 1 over 0.5. So whatever you get there will be your answer in ohms. And another thing is this, when you're calculating your total resistance, always be careful to know the unit of the resistance in the circuit, the resistance of the resistors in the circuit. If you see something like 5k ohms, please, this k is 1000. So 5 kilo ohms means 5000 ohms. Don't just carry 5 and say you want to use 5. So it's 5000. If this is 2 kilo ohms, this is 2000. We'll be looking at examples so you understand it better. All right, we'll be looking at examples so you understand it better. So basically, now if you want to now calculate the individual current for the different resistors, knowing that in parallel connection the current are different. Now I will be equals to, okay, remember that V is equals to IR. So if V is equals to IR, you want to make this guy so to formula to be V over R. So this will be V all over R1. Okay, I1, I2 will be V over R2, while I3 will be V over R3. Continue it, we have I4, it will be V all over R4. So basically, what are we saying here? What we are trying to establish here is that this voltage, I'm not writing V1. Why? Because the voltage across the resistors that are connected in parallel are the same. All right, so just like remember when we are calculating the voltage, the current rather, okay, the current, when we are writing the current for series, I did not write I1, I2. Why? Because the current is the same. So it's just that total voltage divided by the individual resistances of the resistors. Okay, the individual resistances of the resistors. So now let's just look at examples. Let's look at key examples. Okay, let's look at key examples. So I'll be drawing circuits. I'm drawing circuits for you. and we'll be solving them. All right. Now let's say we are given a circuit like this, a series circuit, and it has a battery, let's say of 50 volts, and this is 2 kilo ohms, 1 kilo ohms, and 4 kilo ohms, and you're told to calculate the total resistance. How do you go about it? Very simple. Please continue watching this video. All right, there are lots of things I'm going to be showing you. All right, so basically your total resistance req now becomes 2 kilo ohms plus 1 kilo ohm plus 4 kilo ohms. Okay, 2 plus 1 is 3, 3 plus 4 is 7. So 7 kilo ohms is your total resistance. Now that's number one. Then let's say secondly, you are told to also calculate the amount of current that is flowing through the circuit. Now the truth is this: it is the same current that is flowing through all the wires here. So now I remember V is equals to IR, right? V is equals to IR. So it means that your I will now be V all over R equivalent. I told you. Now your V here is 50. 50 divided by 7 kilo ohms. I told you that 7 kilo is thousand. All right, kilo is 1000. So it's very important for you to state that particular value, all right, in terms of thousands. If you see milli, something like milli means 10 raised to power minus 3. It is commonly used for current. Okay, so 50 divided by 7,000 will give you 0. Okay, let me calculate it again. 50 divided by 7,000, okay, will give you 0.0071. All right, okay, so you now have 0.0071, which is equal to 7.1 times 10 raised to power minus 3 amps, or 7.1 milliamperes. Okay, I told you that milli is 10 raised to power minus 3. All right, so you can you can just state it as 7.1 times 10 raised to power minus 3 is still fine, but stating it as milli in terms of milliamp will also help you to understand how to make use of these milli, nano, pico, okay, and all of that. Watch my video on series and parallel connection. All right, but if you want to know about parallel connection, watch that video. So I'll be giving you more complex ones. We'll be looking at more complex ones. Okay, all right. So now let's look at the circuit setup like this. Let's look at the circuit setup like this. Okay. Okay, so this is the circuit setup. You look at this circuit, you look at it clearly and realize that you have about 6 resistors, and the circuit looks a little confusing if you don't know how to resolve circuits like this. This is more like a combination of series and parallel. All right, so now look at 1, 2, 3, 4, 5, 6. 6 different resistors. All right, 6 resistors here, and of course a battery of 46 volts. Okay, so how are we going to resolve this? Now, first of all, it's important for you to identify the resistors that are actually parallel to each other. Resistors that are parallel to each other, resolve it to series. Okay, now basically this is how we are going to do it. We are going to resolve these two. These are parallel resistors, so we resolve these two. Now basically, if you look at these resistors, we have 6 ohms and 4 ohms. All right, 6 ohms and 4 ohms. These ones are not in kilo ohms, so there is no need doing 1000 times 6 and 1000 times 4. So they are parallel, so basically we have to resolve them. So resolving them, are 1 over r will now be equals to 1 over 6 plus 1 over 4. If you add this, to give you 0.41667. All right, now you know, now I remember I told you, now your arrow now will now be 1 over this guy, 0.41667, which will give us 2.399 ohms, or 2.4 approximately. Okay, 2.4 approximately. So you have 2.399 or 2.4. So you've been able to resolve these two. Okay, you've been able to resolve those two. So now, what you need to also do is that now, after resolving these two, Okay, you will now see something like this. You will now see that here would this place now will combine to form this. All right, this will be 2.399 ohms. Okay, and you have your normal, your 8 ohms here, your battery, then of course your 4, then your 3 ohms. Now to here, your diagonal resistance is still like this is what you have now have. Okay, this is what you now have. So now if you realize it very well, you will now see that these two now are in series. These two that you actually combined in parallel to get the equivalent resistance, now they now form this to be in series to this. All right. Okay, so now you have to solve these two in series. Remember, this is your 8 ohms, this is still 46 volts, this is 4 ohms, this is 12 ohms. As I solve, I'm going to be cleaning because of space. Okay, then this 2.399, these two are now in series. So what do? You just add both of them. Okay, since they are in series, just add both of them. So you now say your arrow now for these two will now be 2.399 plus 3, which will give you about 5.4, about 5 point, yes, 5.4 ohms. Okay, so when you add it, you have 5.4 ohms. So it means that now you've been able to resolve this, all of this now, okay, to be in series. Okay, you've now been able to resolve all of them to be in series. So it means that you will have this, okay, and this will be 5.4. Okay, so permit me to clean this so we can have space to continue drawing our circuits as we resolve. All right, remember this is still 8 ohms. Okay, now we have 5.4 ohms here. We have 5.4 ohms here. Now let us come to this end. Let's come to this end. All right, so now if you look at it very well, you would also realize that, okay, that this 5, okay, and 4 at this point, 5.4 rather, and 8, or 5.4 and 80 ohms, and 5.4 and 4 ohms, okay, they are separated by this diagonal 12 ohms. All right, so it's important to remove this diagonal so we can now have a clearer picture of it. Okay, so basically these 12 ohms and 5 ohms are also in parallel, they are also parallel to each other. These ones are clearly parallel to each other, so we have to resolve our 12 ohms, okay, and our 5.4 ohms that are parallel to each other. And how do we do that? To get a new resistance, okay, parallel, okay, we know is of course 1.12, okay, plus 1.54, 1 over 5.4 rather, 1 over 12 rather, plus 1 over 54. Sorry about that. So basically it's just, okay, 1 over 12, 1 over 5.4. That is the setup for these two that are in parallel. All right, so if we solve that, if we solve these two in parallel, we are going to be having 3.724. All right, 3.724 ohms. Okay, solve it, you have 3.724 ohms. So it means that you've been able to resolve these two that are in parallel. Now please, it's very important to resolve parallel resistors first. Very, very important, because series is very straight. Okay, basically the principle for the resolution of parallel resistors is more complex than that of series. So that's why it's important that in the circuit resolve the series, resolve the parallel rather first before you resolve the series. But if there is a clear resolution for series, also resolve the series. But when you have parallel circuits, parallel circuit resistors that are actually parallel to each other, try and resolve them. Okay, so 12 and 5.4 are parallel to each other. So when we resolve, we have 5.724. So it means that having 3.724. So having 3.724 now, it means that we've been able to remove this guy, this 12 ohms. All right, so it means that we have this, okay, then we have 3.724, okay, Then coming down here, okay, at this point now, we are supposed to now come here. Okay, at this point here, we have our 4 ohms. We have our 4 ohms. Okay, then we close it. So now, if you look at it very well now, we have two different circuits. But by the way, mind you, we have this. We still have our 8 ohms here. Oh. Please, let's not omit that. We still have our 8 ohms here. So we have now we've now been able to resolve the 12 and the 5.4 that we had to form this guy. All right. So this is what we have at this point. Okay, this is what we have at this point. Now, it's very important now to see clearly that 8 and 3.724 are in series to each other. They are in series to each other. So we now have to resolve 8 and 3.724. Okay, mind you, this 4 is not in series. 4 is in parallel to this, but these ones are clearly in series. So we have to resolve these two, so we can now solve in parallel to this guy, because these two are clearly close to each other. All right, so if we resolve this now, we'll have a new resistance of 8 ohms plus 3.724, okay, which will give us 11.724 ohms. So at this point now, it means that we now this one is now we've been able to resolve this with 3.724. We've been able to resolve our 8 ohms. So it means that we have our 11.724 ohms now. So it means that both of them are parallel to each other. And what do we do now? We solve them in parallel. So remember, now our final equivalent resistance now will be 1 all over 4 ohms plus 1 over 11.724 ohms. Okay, let me clean this. Now, by the time we do this, our final answer will be 2.98 ohms, or approximately 3 ohms. All right, so that is our final answer for resolving this particular circuit. Okay, so go over the video again and try to understand it. Okay, just in case you're trying to comprehend, it's very easy to comprehend. Okay, we resolved the ones that those two that were in parallel. All right, we resolved the first ones that were in parallel. That was the one that, okay, we actually had, okay, to resolve. And when we resolved it, we had the whole different. If you look at the video, you realize that I was drawing the circuits as I was resolving. Okay, I was drawing the new circuits as I was resolving. Okay, when we resolved and we had our 2.4 ohms. Okay, when we resolved and we had 2.4 or 2.399 ohms. Okay, and of course we went forward to resolve that 8. Remember, the 5.4 rather and 12 were separated by 8. We needed to remove that barricade. Okay, we needed to remove that barricade, so we solved 5.4. Okay, you remember how we got 5.4 now? We solved for 6 and 4 that were in parallel, and then after solving for 6 and 4 that were in parallel, we now did it with 3 that was in series, and it gave us 5.4. So we now had to do 5.4 and 12 ohms, which were parallel to each other, okay, which gave us 3.724. So now we realize now that 3.724 was now in series to 8 ohms, because we had now been able to remove that 12 ohms, okay, that was blocking the 8 ohms. So now 8 ohms and 3.724, we have to now do it in series. Okay, and when we did it in series, we just added them straight. Okay, remember, we just added them straight, and when we added them straight, we had 11.724. So 11.724 was now parallel to 4 ohms, and we now solved it and we got 2.98, approximately 3 ohms. We'll be looking at another exercise quickly. All right, so this is another circuit we are going to be resolving. So we have a total of 1, 2, 3, 4. We have 4 resistors here. Okay, and of course we are told to determine the total resistance here. Now remember, I told you that it's important for you to first of all resolve sometimes, so not all times. Okay, I told you that sometimes you resolve parallel first, then In cases where series are very close and very clear, okay, the closer the series connection, the more likely for you to resolve it first. Now, if you look at this, you have 6 ohms and 4 ohms to be in series. Okay, now R1 is parallel to R2 because they are not in the same wire. This R2 you're seeing is also parallel to R3. It's also parallel to R4. So if you look at it now, R2 now is parallel to all of them. So since it's parallel to all of them, it's complex. So which one now do you now have to resolve? Do you resolve R2 with R1 or R2 with R3 or R2 with R4? So first of all, resolve these two. Okay. By the time you resolve these two, okay, you will now realize that it will now be parallel to this guy. So you can be able to clearly see that it is parallel. Then you resolve both of them in parallel. So first of all, let us resolve R3 and R4 in series. So R3 plus R4 in series will just be 6 ohms plus 4 ohms, which will give you 10 ohms. Okay, so it means that at that point here, at this point here, you've been able to resolve these two. Okay, you've been able to resolve R3 and R4, and you now have one resistor here which is 10 ohms. Let's just call this R5. This is the fifth resistor where it's not as if it will affect anything. You can call it anything you want to call it, but in order for us to just give it a name, let's call it R5. So if you now look at it now, both of them are in parallel, R2 and R5. So resolve R2 and R5 in parallel. So we have 1 over R2 plus 1 over R5. So this will be 1 over 10 plus 1 over 10. Okay, when you solve this, you use LCM, so you get 2 over 10, which is 1 all over 5. So you know that 1 over 5, by the time you take the inverse again, so 1 over 5, this will now be 5 over 1. That is inverted. Remember, you have 1 all over 1 over 5. Okay, 1 over 1 over 5, which is 1 over 1 times 1 over 1 times 5 over 1. Okay, so basically if you take the inverse of that now, you'll be able to get 5 over 1, which is at this point now you have 5 ohms. All right, so it means that now you've been able to resolve these two. Okay, you've been able to resolve these two. Okay, at this point, remember you have 7 ohms left, so you've been able to resolve those two. Now you now have this, you now have 5 ohms. If you look at it very well, you realize that 7 ohms and 5 ohms are now in series to each other. So it's very simple now. So you now say, let's call this R6. So now you now do R1 plus R6. So the final resolution is 7 ohms plus 5 ohms, which will give you 12 ohms as your final answer. All right, so that is the final equivalent resistance for the circuit. Okay, so guys, we'll be looking at capacitors now. So these are different circuits, but we have to first of all lay a foundation of what capacitors are. Capacitors are devices which stores charges in a circuit. So they are not like resistors that resist the flow of current. Their own function is to store electric charge in a circuit. Now we'll be looking at how they are connected in series and parallel. This is series connection, this is parallel connection. Now the series connection is just like opposite of resistors when it comes to total capacitance. By the way, rather, capacitance is measured in farads. Farads, farads. That is this F you're seeing here. That's the symbol. Okay. So basically, when we look at capacitance, all right, it's very important to know that the total capacitance is like the opposite of that of resistance. How? What do I mean? Now, when you want to calculate the total capacitance in series, okay, in series connection, so basically we want to look for the total capacitance for all these four circuits. So now let's start with this one. So to solve total capacitance in series is actually just like the one in parallel for resistors. Okay, what do I mean? Now look at these guys. Look at this. We are only told to look for the total capacitance. All right, total capacitance. So it is basically 1 all over C is equals to 1 over C1 plus 1 over C2 plus 1 over C3 plus dot 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 1 over Cn. So remember that for resistors, okay, when you're calculating total resistance, you do 1 over, okay, but that is how it is for series. In resistors, 1 over is parallel, but in capacitors, 1 over is series. Why? If you're adding it straight, it is parallel for that of capacitance, okay, and series for that of resistance. It's just opposite. All right, so if we are to solve this, we'll have 1 over 2 plus 1 over 9 plus 1 over 5. All right, so 1 over c will give us 1 over 2 plus 1 over 5. All right, or plus 1 over 9 plus 1 over 5. All right, so when we solve that, we'll get 0.811. So 1 over c will be equals to 0.811. So it means that c now will be equals to 1 over 0.811, which will give us 1.23 farads. So that is the answer for the first one. Okay, so you can pause the video and put it down while let's solve the second one. Okay, let's solve the total capacitance for the second one. All right, for the second one, okay, total capacitance for the second one is just basically adding straight up, just adding. All right, so it's they are all in parallel. Look now, they are not in the same wire, they are all in parallel. This is the battery, but we are not told to look for the voltage or the charge. Mind you, in capacitance, q is equals to cv. This is the charge that is being stored, q, in coulombs. This is the charge measured in coulombs. Then capacitance, I told you, is measured in farads. Voltage is still measured in volts, doesn't change. Okay, so please take note of that. And one thing you must also take note of is that when you're for capacitors connected in series, they store the same charge but have different voltage. While for capacitors stored set in parallel or connected in parallel, they have the same voltage but store different charges. All right, so take note of that. So now let's solve for this. All right, so quickly solving for that now, would have, okay, we would have 1 all over, okay, sorry, not 1 over because it's in parallel. So this 2 farad, our ceq, basically will be equal to 2 farad plus 1.5 farad plus 16 farad, then plus 10 farad. If we add all of this, we'll be getting 29.5 farad. All right, as our total capacitance. Okay, total capacitance. So now let's quickly go ahead to work on this is c1, mind you, this is c1. All right, so I'll be cleaning this. So the answer to this is 29.5. So we have done the first and the second. Let's quickly go to the third one. All right, let's quickly go to this one, then we'll solve that one as the last. All right, so let's quickly solve this. All right, so if you look at this circuit, you realize that two circuits here, two capacitors here are connected in parallel. So it's important, these ones are clearly connected in parallel. Resolve them first. So we have to resolve c1 and c2, which are in parallel. Remember, so it will be c1 plus c2, which will be 2 nanofarad plus 4 nanofarad, and that will give us 6 nanofarad. So we have to resolve these two first. So now as we have resolved it, we'll now have something like this. Now have this is what we now have. All right, so we now have 6 nanofarad, 2 nanofarad, and 4 nanofarad. We have resolved it. So we've been able to bring everything now to form these three. All right, and they are now in series, so it will be very easy now. So remember, in series now is 1 all over c, that is our final equivalent capacitance, 1 over c eq all over 1 over 6 nanofarad plus 1 over 2 nanofarad plus 1 over 4 nanofarad. If we should add this, we'll be able to get 0.916. okay, 0.1916. all right, so then it means that to make ceq, this is still 1 over ceq, then we make ceq, so the formula will have 1.09 nanofarad as our final answer. Okay, because we will now have to do 1 over this. Remember, to make ceq, so the formula, this one will now go here, this one will come here. So ceq now, your calculator, check it to give you 1.09, and we have nanofarad. Mind you, nano is 10 raised to power minus 9. All right, nano is 10, pico is 10 raised to power minus 12, micro like this is 10 raised to power minus 6, milli is 10 raised to power minus 3. Don't forget. All right, so that is that. So now let's quickly do the last one, the last but not the least. All right, please don't forget to subscribe to this channel. Okay, once you're done watching this video. All right, if you have any questions whatsoever, feel free to ask your questions in the comment box below, and of course answers will be provided. I'll provide answers to them. Okay, so now let's quickly resolve this. All right, so this last one here, okay, this last one here is actually we have about 50, we have 50 and 70. All right, in parallel we have these other ones too as well. Let me do this. Okay, now so basically I'm going to be explaining how we'll go about this particular circuit. Now the first thing is to resolve these two. Okay, resolve these two that are in parallel. All right, so resolving these two that are in parallel, so C will be equals to 50 microfarad plus 70 microfarad, so we'll be having 120 microfarad. All right, so when we have resolved this, okay, when we have resolved this, now we will now have this one and this one in series. So we'll now have something, we'll now have this 120 microfarad, okay, and 60 microfarad in series. Okay, let me clean it and bring it closer here. So okay, so it will be more spacious. All right, so this is 120 microfarad. Okay, then here is 60 microfarad. All right, here is 60 microfarad. As we have done this now, both of them are now in series. It's the same wire, but mind you, we still have our 20 microfarad here. All right, then coming down here to this point, okay, to that point we have 120. We have 120 microfarad. That is 120 microfarad over there. Okay, then we have this, then of course the output. Okay, so basically this was, so these two now are in series. This is now one wire, so we now have to solve these two in series. So if we solve it in series now, remember it will be 1 over C equals to 1 all over 120 plus 1 over 60 microfarad microfarad. All right, so once we do that now, we'll have 0 point, if we add this we'll have 0.025. If we do 1 over 0.025, we'll have 40. Yes, we'll have 40 microfarad, because you know you still have, don't forget, once you add this, don't conclude, because you still may need to make sinusoid to a formula. So do 1 over this. All right, so when you do 1 over this, you get 40 microfarad. All right, so now after getting your 40 microfarad, all right, it means that you've been able to resolve this. Okay, be able to resolve this. So okay, so now you will now have this, you will now have 40 microfarad now, right? So you now have 40 microfarad. All right, 40 microfarad. Okay, okay, it's going to be here, it's going to be here. All right, yes, it's going to be here. 40 microfarad is going to be here. Yes, so now if you look at it very well, all right, this 40 microfarad is now parallel to 20 microfarad. All right, it's parallel to 20 microfarad. So if they are parallel to each other, it means that you just have to add them straight up. So now adding them straight will be 40 microfarad plus 20 microfarad. That will give you 60 microfarads. Okay, that will give you 60 microfarads. So you will succeed now in resolving these two. So by the time you have resolved them now, okay, you have resolved these two, you now have to put it here. So now you now have 60 microfarad. So now if you look at it now, these two are now in series. This one wire, they are now in series to each other. They are no longer in parallel. This one wire, okay, this one wire, so they are in series. Look at it now, there's nothing separating. Okay, they are now in series to each other. Okay, so looking at the fact that they are in series to each other, now we now have to Now I have to solve them in series. So this will now be 1 all over 60 microfarad. Okay, so we now have 1 over, sorry, let me get a better marker. So we now have 1 over 60 microfarad plus 1 over 120 microfarad. Okay, so that will give you 0.025. Then 1 over 0.025 is going to give you 40 microfarad. So this is your final answer. That's your final answer. So you've ended up resolving this circuit, and the answer is 40 microfarad. All right, so that is that. Okay, the next one is supposed to be inductors, but inductors very simple. Inductors are just like resistors. So study inductors exactly like resistors. Okay, so they are connected the same way resistors are connected, in series and in parallel, just the same way. The only thing is that inductors, they store, they more like, they are more interested in magnetic charges. They store magnetic charges in the circuit. All right, so they are just like resistors. And of course, the I told you that the symbol is like this, and the SI units for inductance is Henry, H. All right, the just like we have R as resistance and C as capacitor. For capacitance, for inductance, it is L. All right, it is L. So don't forget that, so take note of that. So do well to share this video. Okay, this is basically every calculation, major calculation under basic instrumentation, which is SLT 104.2. Okay, subscribe to this channel, and of course like this video, and also comment if you have any question whatsoever. All right, thank you and have a nice day.